right, so here's example 10 that we weren't able to finish all the way in class, but I want to make sure you got. So remember, we're talking about modeling the number of daylight hours in Paris. So the table here gives us the average number of daylight hours in Paris each month. We let y represent the number of daylight hours in Paris in month x to find a function of the form of y equals a sine of b times x minus c plus d that models the hours of daylight throughout the year. Alright, so the first thing it wanted us to do then was to plot the values in the table and sketch a function that models a graph. And so we did a real quick sketch in class, and that's all I'm going to redo here. And so I have my x and my y-axis. We know our x-axis is our months. Our y-axis is the hours, the hours of daylight? The daylight hours, yeah, that's how we worded it. Alright, and then if you sketch your points, it said we were going to go all the way to 12. Whoops. For my x's and my y's, we were going to go from like 8 all the way up to, I think it was 17. And then we just plotted our points, starting with month 1, which was January, which was 8.3. We go up to 16.1, which is June. And then we came back down because we know that the next January we should be at about 8.3 again. And so we can tell that our graph is has a sinusoidal curve. We also know this is going to repeat itself because we expect about the same number of hours of daylight each month every year. Alright, so we have that there. And then they wanted us to write the equation for it. So to write the equation, and it said to write it in the form of y equals a sine of b times x minus c plus d. So we need to go find a, and remember a is our amplitude. And we said our amplitude was the maximum minus the minimum divided by 2. So my maximum is 16.1 minus the minimum of 8.3, and we're going to divide that by 2. So when we do this, we get 3.9. Then we went ahead and found D. D is that vertical shift. And so we're going to take our maximum, which is 16.1, and we're going to subtract our amplitude. When we do this, we get the midline there, the axis of the wave, at 12.2. Then to find our B value, we know that the period is equal to 2 pi over b. And well, my period, since this is going to, the daylight hours is going to be the same every month, every year, my period is 12 for the 12 months. Oops, I forgot my over b. Sorry about that. So 2 pi over b. So 12 is equal to 2 pi over b. Multiply by the denominator. So we get 12b equals 2 pi divided by the 12, and we get b is equal to pi over 6. So what we have so far for our equation is that y is equal to a, which is 3.9, sine of b, which is pi over 6, times x. We don't know c yet, so I'm just going to put minus c, and then plus our d, which we said was 12.2. Alright, so when I look at this, I've got 3 variables still. I have y, I have x, and I have c. Well, I know I need to solve for c, but if I had an x and a y, then I could do that. Excuse me, so we're going to pick a point. We could pick any of those points, but I'm just going to pick the maximum. And so I'm going to pick the point 6, 16.1. And I'm going to plug this in. By plugging in an x and a y, it will allow me to solve for c. So when I do that, now I've got 16.1 equals 3.9 sine pi over 6 times x is 6 minus c plus 12.2. And so we're just going to slowly solve for c. Now c is inside the sine function, so we got to get that by itself. So let's move the 12.2 over. And so when I do that, we're going to get 3.9. Divide by the 3.9. And so coming back up here to the top now, we have 1 equals sine of pi over 6, 6 minus c. Alright, so I'm going to take a little side note for a minute here. If I let this just represents some angle, so I'm going to let it be theta. So that means we have 1 equals sine of theta. Well, we know from before on our unit circle here that sine is our y values, and so I'm looking really for where y is equal to a positive 1. Well, y is equal to positive 1 right up here at pi over 2. So what you just told me then, the angle is going to be pi over 2. But now backtracking, you told me that we were letting this be our angle, and now our angle equals pi over 2, so we can set them equal to each other. So we know that pi over 2 is equal to pi over 6 times 6 minus c. And now we're just going to solve for c. So first let's get rid of the pi over 6. Remember, you can divide by it, but that's the same as multiplying by its reciprocal. So I'm going to multiply this side by 6 over pi, and same thing over here. So on the right-hand side, the left-hand side there, my pi's will cancel. 6 over 2 is 3, equals, on the right-hand side, pi's cancel, the 6's cancel, and I get 6 minus c. So now I'm just going to solve for c. So negative 3 equals negative c, divide by the negative 1, and so we know c equals 3. And then we're just going to put it all back together and write our equation, because now we can take this c equals 3 and we can plug it back into our equation up here. So I'm going to have to write it down here at the bottom. Our equation then is going to be y equals my a, which is 3.9, sine of our b, which is pi over 6, times x minus c, so it's just 3, and then plus d, so plus the 12.2. And there is the equation of our graph. And we can check that, which is what it wants us to do on the next slide. I'm not going to change it here yet. So it also, well, it doesn't tell us on the slide, I'm sorry. And it actually doesn't tell us on this one. But if you wanted to, you could actually take this equation and put it in your y equals. You can take the table that they gave us at the very beginning and go put it in your stat edit. Make sure you turn on your stat plot 1 and then graph it. You can either set your window or you can use your zoom stat thing to be able to look at the graph. You should see that your equation lies very close to all of your points. It may not go through every exact point, but it should be really close to them. All right, so that's the end then of our example 10.